Okay, so right, the subject of this talk are harmonic maps between manifolds, and I'll remind you just of the basic definition of what they are first. So for smooth maps, we define the energy integral, where you just integrate the derivative with respect to the metrics on the manifolds M and N. And providing that this is finite, which is going to be the case when manifolds are compact, say, then you can talk about the stationary points of this functional and stationary with respect to a fixed homotopy class, or which, providing the manifold has a boundary, it means relative to the boundary. So the boundary is being kept fixed, not just the homotopy class inside of the manifold. And the stationary points are called harmonic maps, should they exist, of course. Well, harmonic maps are generalizations of harmonic functions, and in geometry they first arose, if I understand this well, as in the study of hypersurfaces of constant mean curvature. And the reason is that is this very old result, is that the hypersurface, well, a surface in R3 has a constant mean curvature if and only if its Gauss map is harmonic. So Gauss map, it maps the surface into S2, and right. Interestingly, it took a long time to generalize this theorem to something else, meaning to some other setting beside the Euclidean space and surfaces in the Euclidean space. And an important result has been proved about like 25, 30 years ago, which replaces the R3, the Euclidean space, with the Minkowski tree space, and they're the constant mean curvature surface. Well, if you take one, well, you have to prove it exists, but they do. People constructed them, and then their Gauss maps would produce harmonic maps from the surface, but this time not into S2, but into the hyperbolic plane. And these were, in fact, these were the first examples of kind of interesting harmonic maps into the hyperbolic plane, beside those that are coming from closed surfaces and the coverings. So, well, I said that these harmonic maps are stationary points of the functional, but you can compute their Euler-Lagrange equation to get some PDE that governs these harmonic functions and maps. So first of all, when the target is one-dimensional, which is meaning the real line, then well, harmonic maps are called harmonic functions, and they satisfy the famous equation that the Laplacian is equal to 0. So Laplacian is computed, of course, with respect to the metric on M. So more generally, the next stage where you can see kind of more clearly this equation is when you have map between Riemann surfaces endowed with metrics. I did not put the metric on M here because, interestingly, in dimension 2, harmonic maps do not depend on the choice of the metric in the domain, as long as the metrics are conformal. And well, because we are in the Riemann surfaces and I like complex analysis, then you can write this in the complex form. So this is, well, it's really two equations if you use real notation, but complex notation makes it possible to put it into one equation. So this is the equation for harmonic maps between Riemann surfaces. Kind of an equivalent way of saying that f is harmonic is that this expression here, a rather simple expression, is a holomorphic quadratic differential on M. Now, you can check that this is certainly a quadratic differential as a form on M. It's that kind of form, but that's true no matter whether f is harmonic or not. But it's going to be harmonic F is going to be harmonic if and only if this is holomorphic. And more generally now, you can define the harmonic maps between two Riemannian manifolds this time. And to do that, well, one way you can think of it is to define what's known as the tangent field, and then say that map is harmonic if and only if the tangent field is 0. So if you're not familiar with this, we should think of this tangent field in a physical sense. Namely, I wrote the definition of it here, but it's a vector field. So as an object, it's a vector field that lived essentially in the target manifold. Well, if the map F is not surjective, then you really need to pull back the tangent bundle of n back to M, and you define the vector field there. But should F be, say, a diffeomorphism, then this tau of F is a vector field on the target. And whenever you have a mapping, you can define this vector field by this formula. And the role of the geometric meaning of this vector field is that if the vector field is non-zero, if you deform the map along this vector field, you're going to decrease the energy that was put on the first slide, which means that if this guy is not 0 tau, then your function is not the stationary points of the energy integral. So therefore, it's natural that map is harmonic if and only if this vector field is totally 0. It's interesting, and you'll see later, that this vector field comes completely naturally out of a different computation in differential geometry, completely not unrelated to harmonic mappings. And that's actually really important for all the results in this talk. Okay. So, as I said, harmonic maps satisfy the equation that the tangent field is everywhere 0. And I explained to you about deforming it. Okay. So now that we settled on what harmonic maps are, let's see why are they interesting, or well, some subset of reasons why they would be interesting. And I just here restricted myself to applications of harmonic maps in kind of geometric topology, which really means in rigidity problems. Of course, harmonic functions and maps are playing a huge role all over mathematics, especially harmonic functions. But they, in this subset of mathematics called geometric topology, they are usually used in rigidity. And example of that, the first example I want to mention is the C rigidity theorem, which says that the Kähler manifolds, if they are homotopy equivalent with symmetric space, well, symmetric Hermitian space, then in fact they are symmetric Hermitian space. There is a biholomorphic map. So in other words, the rigidity theorem, it means that you cannot deform them. And all the rigidity theorems have this kind of flavor to it. And this is maybe the first one that came about. And usually the proof is like this. You show, well, you start with this homotopy equivalence by doing some work. You show that this homotopy equivalence is essentially realized by harmonic maps, which is not hard to, it's not hard to contemplate that such a thing should be true, because you can start with something realizing the homotopy equivalence and then minimize the energy integral, and then with some work show that the minimizer exists, and then it's going to be a harmonic map. But then there is a collection of formulae in this theory called the Bochner formula, which are certainly best known for harmonic maps between surfaces. For example, they can be derived in that case from this notion of the Hopf differential that I told you about a minute ago. But more generally, they work on Kähler manifolds, and using those formulae, one can show that such a harmonic map in this situation has to be biholomorphic, which is then realizes this biholomorphism between a Kähler manifold and its Hermitian locally symmetric space. Another example is this Collet-Gromov-Shan proof of the p-adic superrigidity of lattices in groups of rank 1. It is essentially generalization or a form of Margulis superrigidity theorem, which says that, well, this kind of theorems say that if you have a representation of a lattice from a high rank Lie group into another high rank Lie group, for example, that underlying Lie group itself, that such representations extend to the whole Lie group. In other words, there is no deformation space of lattices in high rank Lie groups. And this is kind of a special case of this, but it's really not about rank 1. So it's not about high rank. This is still in rank 1. So generally in rank 1 you do have deformation theory. That's called the Teichmüller theory. You can deform lattices in PSL2R and PSL2C, but in these rank 1 Lie groups corresponding to quaternionic hyperbolic space and the Cayley plane, you cannot do that if you're speaking about these lattices of this form. So again, in this case, the underlying, so why this is also interesting is that the harmonic maps here, well, in the previous example you had a harmonic map from a Kähler manifold into a Hermitian locally symmetric space. Here harmonic maps are defined on the associated Euclidean buildings which essentially have metric space structure. They are not manifolds. And this is an example where a generalization of harmonic maps from manifolds to metric spaces that's been done by Shan and Gromov at some point has been used successfully to prove this rigidity result. Well, I won't say why, but harmonic functions and maps figure in Kleiner's proof of the Gromov's theorem on the polynomial growth of virtual nilpotent groups. And another example, kind of in Teichmüller theory, there are some applications. So these are not rigidity statements, but so harmonic maps can be used to parameterize Teichmüller space of a Riemann surface, basically by choosing a harmonic representative in each homotopy class. Then you take its Hopf differential, which is now a holomorphic quadratic differential, and that gives you a parametrization of the Teichmüller space. Now the reason that turned out to be important is because this is by far the best way to understand, at least analytically, the Thurston boundary of the Teichmüller space. And Mike Wolf, a long time ago, done this analysis. He established a pretty good control on how this Hopf differentials degenerate when the complex structure in the Teichmüller space degenerates. So that was really significant, I believe. Well, the kind of problems that we want to talk about here are existential problems. In other words, whether harmonic maps exist, and we also want to mention something about the uniqueness. Now, well, the Dirichlet problem is an ancient problem in mathematics, and it's about, in its more rudimentary form, it's about whether you can extend a continuous function from the boundary of the unit disk onto a harmonic map inside, a function inside. And this is easily generalized to manifolds and prescribed homotopy classes, and the question whether prescribed homotopy class contains a harmonic representative. And as long as the manifolds are compact, this problem has been really well understood, but it took quite a while. And from the pioneering work of Ilse and Samson, who managed to solve this problem in many cases, essentially it was Richard Hamilton who completed the study, proving essentially this theorem here in his book on the field, on the subject. So yeah, so a lot actually goes into this proof. It's a serious mathematical theorem. But the point is that the problem is solvable, and you can do it uniquely, in fact, as long as the manifolds are compact and the target has non-positive curvature. And if the target has negative curvature, then the solution is unique, and otherwise may not be unique. So clearly, when the target has zero curvature, for example, torus, there are many homotopic biholomorphic maps of the torus to itself, and therefore many harmonic maps homotopic to the identity. But otherwise, the problem has this solution. So the Dirichlet problem is solvable on compact manifolds. And now, trying to understand other cases, for example, when the target, the domain is not compact anymore, you can start with functions, and the functions for the problem for functions has positive solution. So this is a theorem proved independently by Mike Anderson and Dennis Sullivan sometime in the 80s. So you start with a negatively curved, simply connected Riemannian manifold, for example, hyperbolic space, or more generally, and this is kind of the Bain example, if you take a closed, negatively curved manifold, take its universal cover, that's an example of a manifold I want to talk, manifold M in this statement. Now, you can, because this is negatively curved, the boundary has a well-defined structure and so forth. So you can talk about continuous functions on the boundary. Now, you can talk about the Dirichlet problem then. Can I extend this harmonic function, continuous function to a harmonic function? And the answer is yes. That's what this theorem says. So this is particularly interesting because Sullivan gave a probabilistic proof of this result. Anderson gave a very technically complicated PDE kind of proof, but Dennis gave a very simple proof by basically proving a conjecture of Yau. So, right, so what's the plan? Well, if instead of a continuous function on the boundary, you start with say a measurable set on the boundary, like an interval here, and if you take a point inside this space M, then you can think of the boundary map F to be just the characteristic function of the set A. So it's 1 at A and 0 otherwise. I know this is not continuous, but so what? I mean, I'm just going to solve the problem for this guy and then approximate continuous functions by these characteristic functions of this form. Now, the point is that harmonic function at x takes the value which is the so-called hitting measure of the set A when viewed from the point x, which means that you start randomly running random walks from this point x, and then you have a natural measure on those random walks, and then you take the proportion of them that hit the set A. So that's some number between 0 and 1, and that's your value of the harmonic function at x, so-called hitting measure. Right, so when this manifold M is hyperbolic, then this is also harmonic measure, and it's equal to any other nice measure. Right, at infinity, now you can generalize this problem from functions to mappings, and now you have two such negatively curved manifolds M and, well, M and N, and then you have a continuous map between their boundaries. And the question is, can you find a harmonic map, homotopic to this prescribed boundary map? Right, so here we were mapping it into real line, but here we have a map from the boundary of M onto the boundary of N. And, well, it turns out that this problem is not natural. I mean, it doesn't have a solution. It's too general. Everything that you can attempt to prove fails. There are counterexamples for every possible statement. So clearly, something had to be done to make this theory, to develop a proper theory on this level. And the following level of generality, the following question was proposed by Rick Shan, but not just by Rick. probably before him, people like Royden and maybe some others were asking this question in special cases. And in fact, this is not really the question of Shan, this is its generalization. But I'll tell you what Rick asked specifically. So anyway, this is really the question. Now we know that we cannot, if we have put no condition on a homotopy class of the map or the boundary condition, either way, there is no theory. So there is a geometric condition that you can impose on a homotopy class, and that is that it contains, that it's a quasi-isometry. So by that, there are various definitions of quasi-isometry, and I'm using this one. So this is the metric on the target, and then you have metric on the original. So some people call this a coarse bi-Lipschitz map or something like that. Anyway, so you assume that the map, there is a map in the homotopy class satisfying this. So this is essentially, these maps don't have to be continuous. That's why you have this additive constant to exclude the local considerations. But on the large scale, they are basically bi-Lipschitz. And the question is, well, if you have two, well, in the first instance, rank 1 symmetric spaces that are not necessarily of the same dimension and a quasi-isometry between them, can you find a harmonic quasi-isometry representing this mapping? Now, there are not many rank 1 symmetric spaces, and modulo some standard argumentation, this descends to the question about hyperbolic spaces if you ask about rank 1. And essentially the questions are, you have two hyperbolic spaces of possibly different dimension and a quasi-isometry. And the question is, can you realize by harmonic mapping? For example, you can map the 2-plane into the 3-plane, into the 3 space. So essentially, for those who know what a quasi-circle is, that means that if you have some quasi-circle in the boundary of H3 and a parametrization of it by the circle, quasi-symmetric parametrization, the question is, can you extend this to a harmonic map into H3? That would be an example of this problem. So this proved to be a difficult problem, but so we'll get to that, but let me just give you this so-called generalized Shan conjecture, which is essentially the statement of from the previous slide, formulated as a Dirichlet problem, as something on the boundary. The previous formulation had no, it was intrinsic to a manifold, any hyperbolic manifold, or rank 1 symmetric space. And here, so you start with a quasi-symmetric map, and that's more like that example I gave you there. So you say map S1 into S2 quasi-symmetrically, and then you want to extend it to harmonic quasi-isometry that satisfies this boundary condition. So, right, originally Shan conjecture, which was asked before by Hershey-Royden, asked this in the special case when n and m are both equal to 2. So you have a quasi-symmetric function from the circle to itself. Can you extend it inside to harmonic diffeomorphism? That was the original problem. And then people generalized this a few years after the original question appeared in press. They generalized it to rank 1 symmetric spaces. So, as I said, the original conjecture was the 2D problem, and So I wrote a paper resolving this, proving it's true last year. So, right, every quasi-symmetric map from S1 to itself can be extended to a harmonic map. This is because harmonic maps in this situation are unique, as I will convince you a little later. This is really equivalent to saying that whenever you have two Riemann surfaces, whether they're closed or infinite genus or have boundary or whatever, whenever you have two Riemann surfaces and a quasi-isometry between them, then you can find a quasi-isometric harmonic diffeomorphism in realizing that homotopy class. Right. So for example, one consequence of this could be to understand the Thurston boundary for other Teichmüller spaces, not necessarily finite dimensional ones. Should somebody want to study that. What is kind of a cousin to this theory of harmonic functions and maps is the theory of heat flows. And so heat flows are used to construct harmonic maps. I will tell you a little bit later on exactly their definition, but just informally right now, if a map is not harmonic, then there is a tangent field which is non-zero, which is a vector field, and then you start running the flow along this tangent field at each time. So this is called the heat flow. And if a heat flow converges, you should certainly expect that it converges to a harmonic map for obvious reasons. Now, heat flows are very hard to control, and even in the Euclidean case, unless you put very kind of strict conditions on the initial map of the heat flow, you cannot prove the convergence of it. However, with Marius Lemm, we proved the theorem that in fact, whenever, so that's not written here, but it should have been. This only works for n at least 3. This theorem. So in the previous slides we discussed the case n equal 2, but here we have the case n equal 3. And now whenever you have a quasi-conformal map between two spheres, say S2 or higher dimensional, then you can extend this quasi-conformal map inside to a quasi-isometry, which will be initial map for our heat flow, so that then when you run the heat flow, this heat flow will converge to a harmonic quasi-isometry as we were seeking. And yeah, if I tell you more concretely about some mathematics in this talk, it will be about that theorem, because it's perhaps technically less challenging than the other one. So essentially, in my work and my work with Marius Lemm, we've proven this Shan conjectures for maps between hyperbolic spaces of the same dimension. But the case that remained is for to prove the same thing, but now without restriction on allowing different dimensions of the domain and the target. And later last year, this has been done by Benoist and Hulin. So they shown that that this is really true. So I'll tell you a little bit later of how is the connection of their proof with my work. But now let's talk about some mathematics more precisely. So let's now forget everything about harmonic maps, and let's just now kind of focus and think on the following. Let's say I have two functions from the hyperbolic space to itself, and then I set the distance function between them. In principle, in my applications of this, these are not harmonic, these are just arbitrary. These functions, these mappings will have the same boundary values and will be quasi-isometries, which implies then that this distance is uniformly bounded on the hyperbolic space. So you might as well think that at that assumption here. So you have a distance between two functions, two mappings that has an upper bound, and then you derive, well, when you compute the Laplacian of this, the square of the distance, so the square of the distance is c2. That's why I take the square, otherwise it's not c2. But it's c2, it's twice differentiable. And then in differential geometry, that's what they always do. They always compute the Laplacian of the distance function. And then kind of something miraculous happened here. This is a computation that was done by a number of people independently: Carl Jagger, Shan, Yao, some others, I forget. It's kind of the whole, it's like the point of that field is you get such beautiful formulas. And what this formula tells you, essentially, is that the Laplacian of this distance is subharmonic modulo the first term, which is negative. And the first term figures the tangent field of phi and psi. So the tangent field comes here completely from a different angle, not related with the harmonic maps. We know that tangent field is an abstraction to a mapping being harmonic, but here, when you compute this distance, this is the formula you get. And the tangent field is now abstraction to this distance function being subharmonic. Okay. So that's fascinating, and in fact, it was at the beginning of the consideration for all these proofs. This kind of a curiosity, it seemed like a curiosity at first, but right. Let's see the first application of this curiosity. Right. Well, if you have two harmonic functions of the hyperbolic space to itself with the same boundary values, then, as I said, the distance between them is finite. And because they're harmonic, the tangent field vanishes. So the distance function is subharmonic. And then essentially by the generalized maximum principle, it requires a little bit more, but really, I mean, you need to use the fact that there are plenty of isometries on the hyperbolic space. But essentially, once you have that, then you can clearly see that because distance function is harmonic, you would want to find a point where this distance is maximized, but you would expect that at that point the Laplacian will be negative, and that's not possible. So the functions have to be identically the same. So this is how you prove the uniqueness. And in fact, I should say this formula here was stated for the hyperbolic space, but it's true on every negatively curved manifold. And in fact, except the only thing that's going to change is that this constant 2, well, this constant c, rather, will depend on that, but on the curvature. So if it's pinched negative curvature, the constant is uniform in terms of the upper and lower bound on the curvature. And for the hyperbolic space, you can compute it explicitly, which I didn't. But the same principle holds. So you can show the uniqueness of harmonic functions and negatively curved manifolds from this formula. So harmonic functions are much easier to study from the point of view of these existential problems, simply because the equation for harmonic functions is linear, and this for harmonic mapping and mappings is not. And I made an example to illustrate the problem. So the point is that the C1 norm, C0 norm in other words, which is just the standard supremum norm between mappings. In the case of functions, if you have two continuous maps on the circle that are closed in C0 norm, then their harmonic extensions will also be closed in the C0 norm, because the distance is subharmonic and it will be achieved at the boundary. That is not true for harmonic functions, for harmonic mappings, I'm sorry. In other words, there is an example of this nature. So you can approach the identity by harmonic diffeomorphisms of the circle, but their harmonic extensions will blow up everywhere. You couldn't extract any kind of limit. So there is no maximum principle of any kind with respect to the C0 norm. However, it follows from my theorem then that these diffeomorphisms, that their quasi-symmetric constant will blow up. So what this Shan kind of problem is essentially seeking is to somehow bound and control the geometry of a harmonic map in a hyperbolic space by using not the C0 metric of the functions on the boundary, but rather the behavior of their derivatives, or of rather the distortion, which is kind of the weaker form of the of control, weaker than controlling the derivative. You're controlling the distortion of those boundary maps. So somehow, in a subtle way, the distortion of the boundary controls the geometry inside. That's kind of the point. So as I said, this is certainly different than with respect to but what happens with harmonic functions. So the heat flow is here, and right. So if you have a non-zero tangent field, then you just evolve along the tangent field. You get the heat flow, and right, you need the strong assumptions on the initial map to guarantee convergence. For example, there is this whole theory of Peter Lee and Tam and Van and Yao and Shan, where people were trying to understand exactly when the heat flow is going to converge, generally on manifolds. But in negative curvature, this assumption is sufficient. So you need to bound the L2 norm of the tangent field of the initial mapping. Now, if your manifold is compact, then the tangent field will be bounded and the L2 norm will be finite. But if the manifold is non-compact, for example, the hyperbolic space, then the initial map, then this is, of course, of infinite area, and there is no reason to expect, and it will not be true, that for an arbitrary quasi-isometry, you can deform it to something that has an integrable tangent field. That's not going to be possible. For that, in order for that to happen, you would have to, your map would have to become almost conformal as you approach the boundary. So you will see a more quantitative version of this indication I just gave. But anyway, this is this assumption was still sufficient for these guys to prove a version or a special case of these conjectures. Namely, they've shown that this kind of Dirichlet problem is solvable when the boundary map is not quasi-conformal, but something stronger. It's actually a diffeomorphism. So, or more generally, they did it, but I didn't write it here. They allowed the spheres of different dimension and the map to be smooth. So for smooth boundary conditions, you can extend them to harmonic quasi-isometries. And in fact, you can do that by running the heat flow. And the reason is that when the boundary map is smooth, you can extend it inside by hand to a quasi-isometry that has an integrable tangent field, which is in L2. And then you run the heat flow to it, and then you get the result. So the way that works, and I want to mention that here, is by this very important observation by Hamilton. So it turns out that the square of the absolute value of the tangent field of this vector field is always a sub-solution to the heat equation. Right. Well, right. So then by the parabolic maximum principle, you get this inequality where H is the heat kernel on the manifold. So in order to show that the heat flow converges, you want to make this go to 0 at least. In fact, you want to make it go to 0 fast. And so you use this inequality like this. So you apply the Cauchy-Schwarz inequality to the. So here, if it was unclear, look at this last inequality. Apply the Cauchy-Schwarz on the right-hand side, and you get this. You get that the tangent field, absolute value of the tangent field at any given point, is smaller than the L2 norm of the heat kernel times the L2 norm of the tangent field of the initial map. Now this tangent field it's integrable, so this is some constant, and the L2 norm of the heat kernel exponentially decays when the time goes to infinity. And that's a simple proof now why the L2 tangent field of the initial map guarantees the convergence of the heat flow. So as I said, in general, you cannot do this. Maps of the boundary can be much more complicated than the smooth maps, and you cannot extend them to a map whose tangent field is integrable. That's just the point. But you can do something else. So the reason why this heat flow method here works in dimension 3 and higher and does not work in dimension 2 is because of the master rigidity theorem. So by using master rigidity theorem, you can do the following. So given any quasi-conformal map of the sphere, let's say S2 for simplicity, you can extend it inside not to something that has integrable tangent field. In fact, you cannot hope that the tangent field will even go to 0 as you approach the boundary. It will not. You cannot do that by hand. But you can construct such that the tangent field is going to be small at a random point. And what that means is that if you if you start anywhere in the hyperbolic space and start growing a ball around it, then as the ball gets large enough, a huge proportion of that ball will have the property that the tangent field is small at that point. And the larger the ball is, this proportion goes to 1, or it becomes 100% almost. Of course, 1% of something large is still a lot. But it turns out that this is enough to essentially imitate the argument that we just saw that was used by Hamilton. So you don't really need a tangent field to be in L2. It's actually enough that it's small at the random point. That's the point that I'm trying to drive home here. So the way that works, so you need a little bit different computation. But on some level, it's very similar to the Hamilton's original computation. So first of all, let's look at here. So from this Hamilton inequality, you can now bound the tangent field of the heat flow, the square of its absolute value, by this integral. So this is just the product of the heat kernel and tangent field of the initial map written in the polar coordinates. So not to get technical, but anyway, this A of rho is the average you're integrating. So let's say that this is the point x where we begin, where we estimate the tangent field. You draw some large ball around it, and then by the inequality by some kind of Fubini theorem becomes this. The tangent field here is bounded by the integral from 0 to infinity, where you integrate at each row, you're integrating the heat kernel against this average at rho. And the average at rho is you integrate the tangent field along the sphere of radius rho, and you take the average of it. Right. But because of this 99%, because even if the tangent field is not small at large parts of this, it is still small on a huge proportion of the sphere. So this average is going to go to 0. That's the point. So here is, so to get this computation working, you need some very precise estimate on the heat kernel in the hyperbolic space. It turns out that it kind of evolves ballistically. Like you drop a bomb and then it's like a wave supported in an annulus. Not a very thin annulus, kind of a large annulus, but you need precise estimate on how large it is. But thankfully all this has been done by people before. Anyway, I don't want to bother you with these formulas, but once you have these estimates, this is what happens. You can show that this integral goes to 0. And so you show that you have an initial map so that when you run the heat flow, the tangent field of the heat flow goes to 0. Now this is not enough, of course, to guarantee that the heat flow converges, because all you know is that in time it moves slower and slower, but it still can move infinitely in time, right? There are sequences that tend to 0, but their sum is infinite. So it seems that we are we haven't done much by this, but this is what this kind of Hamilton business and master rigidity combined can give us. Yes?
So what you mean by master rigidity is that quasi-conformal maps are almost everywhere very similar in some solid space.
That's right, thank you. So I didn't say what I meant because I wanted to say too many things. Right, so the manifestation of the master rigidity is that they are differentiable almost everywhere on the boundary, which enables you to construct this map which will have this property that the tangent field is small, kind of at a random point.
And for this to work, what you need is that they are in the same, if you have an map which is in the same solid space, you can apply that.
Say that again, I'm not sure I got it.
If you have the same kind of estimates, so
Yeah.
that if you're in the same solid space as quasi-conformal maps,
Yes?
then you can apply that.
That's right, yeah. I mean, the Sobolev space is H2 plus epsilon at least. So that's the that's what you have. Right, but the point I'm trying to make is that all you can do by this, and you cannot do better, you can only know that this goes to 0. You certainly have no, I mean, it's success, it's more than we had before, but we cannot say that this goes exponentially to 0 to guarantee the convergence immediately like we did with our assumption that the tangent field is in L2. We have no control on how fast this goes to 0. So, but at least let's we formulate this in this statement that essentially from Hamilton and Mastow we get that this converges to 0 uniformly. At least it does not depend on the point in the hyperbolic space. It's uniform in points. Right, but we don't know how fast. So as I said, yeah, that's the derivative, because the heat flow is this path. You start from somewhere, so this path slows down, but it still might go who knows where. But then something kind of remarkable happens. Now by using, again using master rigidity in a completely different way, and by using kind of Green formula, Stokes formula, all this kind of formula. So you're doing some kind of series analysis in the hyperbolic space. You can prove the following result. So this is also true only, and it's interesting in its own right. It's only true for n bigger or equal than 3 again. And it says now that whenever you have a mapping of the hyperbolic space, so the boundary map has a control distortion, which is this quasi-conformal constant k. Now we want to fix that, and we want to allow the map inside. We extend it in some way to a smooth map, which has the property that the tangent field is less than some universal constant Cn. It's not 0. It's not, map is not harmonic necessarily, but the tangent field is just smaller than some threshold. Now then, the geometry of this map is controlled completely by the distortion at the boundary. So what that means, it means that the extension is quasi-isometry where the constants of it, L and A, well I use K here, but L would be the meaning of this. L and A are completely dependent just on the boundary map. So this happens as long as you drop below some threshold. Right? I mean, this is fascinating because it's clearly, of course, you can extend the identity map from the boundary to something very complicated and something that blows up inside. But that thing will have to have also a large tangent field then. Because if the tangent field is bounded, or in fact small enough, but just less than universal constant, then the boundary controls, the boundary distortion controls the interior. And this is really important. And I used that a couple of years ago to prove these conjectures in the dimension 3, essentially. That was relying on this result. But now we are in business without heat flow, because what happens is that we have a heat flow that at some point its tangent field is getting smaller and smaller, and at some point it goes to 0. That's what we proved. And then at some point it's going to dip below this threshold Cn. And then I have a different way of controlling the geometry of my mapping. I I'm not proving that this path is finite length. I cannot do that. But now by some different mean, I know that this path, maybe it's going to go a long time, but it's going to stay in some bounded domain. And I will have and then I can use essentially Azrela's Colli to show it will converge, and then it will converge to a unique harmonic map. So this is the point, and this is the proof of this theorem, that the heat flow converges in higher dimensions, and that's how you can show that the harmonic map exists. And in particular, I like this theorem more, although it's easier than the other one in dimension 2, simply because you're actually doing something physical. You have a natural process called the heat flow, and you show it converges. And I still don't know how to do that in dimension 2, and find that kind of a little bit troubling. But anyway, so I have 5 minutes, I suppose. Well, dimension 2. Well, as I said, the heat flow method is not available. Well, the only thing that doesn't work is that you cannot get this, when you have a boundary map, you cannot extend it to something that has a tangent field small at a random point. We don't have this rigidity, and that's just the problem. So this all falls down. But nevertheless, as I said, you can still prove the theorem that every quasi-symmetric map of the circle admits a harmonic extension. And in fact, you can extend it to a harmonic quasi-conformal map. So it's going to be a diffeomorphism inside. While in higher dimension, these extensions, even if the boundary maps are diffeomorphisms, the extensions need not be. For some topological reasons, in dimension 2, this is always the case. So I already mentioned to you, but in this particular case of harmonic maps of the hyperbolic plane, the formulas are this for harmonic functions. And you have this Hopf differential and so forth. And right, so I'm not going to tell you much about how the proof goes, although the proof has similarities with this previous theorem where I shown that the geometry tangent controls geometry. So the techniques are similar, but the punchline is a little different. However, yeah, so actually let me indicate what that would be. So if you choose some base point on the hyperbolic space and set the polar coordinates there, then you can look at the distance function. And well, this formula here, in fact, is a special case of the formula I already gave you. Remember, I gave you the formula where they compute the Laplacian of the distance between two different functions, sine phi of its square. If you take this to be the identity and this to be a constant function mapping it to the origin, then that version of the formula, that computation gives you this. So in particular, this distance function is subharmonic. That's the point. Okay. And now, right, so what's the beginning of the proof of this theorem in dimension 2 is that you start with some quasi-symmetric mapping on the boundary and extend it to some quasi-isometry from H2 to itself, which is some fixed quasi-conformal map, K quasi-conformal. So it has a fixed distortion, and you leave this you choose this and fix it throughout the proof. And then you pretend for a minute that you're in a situation where you do have a harmonic extension, and then you want to understand, you want a uniform upper bound on the distance between f and g, where f is harmonic now, has the same boundary values as g. But you want the upper bound only to depend on this distortion of g, not on anything else. So for example, as I told you already, people know that when the boundary map is smooth, then you can extend it to a harmonic map. So if you get this uniform bound for those, then you can just pass on to limit and get the uniform by approximating. So every quasi-symmetric map can be approximated by smooth ones. So that's how I chose to work. And well, there are. So what I do? Well, I apply. I'm not going to tell you anything about that, but I apply various analytical tools on the hyperbolic space, and there is a very clear reason actually how this inequality is proved and so forth. But once I prove that, then so for some reasons which are so I used in my proof in dimension 2, I used the harmonic differentials, Hopf differentials, and to get a particular inequality there, I used essentially the fact that we are in two-dimensional situation. Well, that was actually completely unnecessary, and Benoist-Hulin, they observed that, and so basically the way they prove their theorem, generalizing this to essentially allowing domain and the target to be of different dimensions, is their proof is in some sense really straightforward. Well, the idea is straightforward. They, unlike me, they don't want to assume that they have a harmonic representative, which they cannot in general, but they replace that by exhausting the hyperbolic space by balls of finite diameter. And then on each ball, they solve the Dirichlet problem. They know that this solution exists. And then they are controlling the distance between the harmonic map and some underlying map G, as I already have here. And the way they do that is that they divide analysis into two parts. One part is they control the distance between F and G when you are near the boundary of this ball. And the second part is when you are not near the boundary, because when the ball is large, there are many points inside of the ball that are not close to the boundary. So they use essentially my proof, some version of it, to those tools to control the distance inside, away from the boundary. But they develop completely new analysis near the boundary. Yeah.
What do you mean by your proof is like the second theorem you mentioned before?
My no, it's this this theorem. Yeah. Right. So first of all, they observe that there is nothing two-dimensional about my proof. Then they construct this exhaustion argument, and then they say, well, what Vlad did really can be modified to control the distance between a harmonic map and some underlying map inside. But then they have a completely new theory of how the distance is controlled near the boundary. So when they get them together, they get the proof. And in fact, their proof works now for in any case. So it's right. It covers every case at once, and that's the beauty of it in particular. So, yeah. Right. So the last thing I want to say is that once you look into these proofs, both my arguments and then what they did, how they utilized that, and their argument near the boundary and so forth, you see that there is really nothing, at least, well, if you look into my heat flow things and so forth, then there are some kind of subtleties there. But if you look at this kind of, in this proof of the existence of harmonic function mappings, you see that actually there is nothing about the symmetric space that plays a particular role. The constant fact that curvature is constant is irrelevant. But what really matters, as I pointed to you in that formula, is that the curvature is pinched negative. And so it's certainly reasonable to make this conjecture, which I believe is true. But I still don't know how to prove it, although I haven't thought about it that hard yet. But anyhow, so you would now think that the right formulation of the Dirichlet problem for Riemannian manifolds is that when the curvature is negative, or say pinched, then there should quasi-isometries should always be homotopic to harmonic mappings. That should be the theorem. Of course, applications may trigger more theorems. You can, and what turns out is that often when you want to apply harmonic maps, you must work not on manifolds but on metric spaces that are nice but are not manifolds. And would be interesting to understand, but I have less understanding of that certainly than of this conjecture. That's why I'm not making any conjecture. But it would be interesting and maybe important, who knows, is to repeat this and see what this gives you when you work on just negatively curved metric spaces. And that's where I'll stop. Thank you.